Three of the organizers are here, Rand Levy, Paul Selleck, and myself, Tony Bari. And Paul is just going to say a couple of words of welcome.
Well, on behalf of the organizers, for those who have just arrived here, welcome to Toronto, welcome to our program, welcome to the Fields Institute. And I don't really have anything more to say. We have our picture of Fred up there. Those of you remember Fred, our program is in honor of Fred. And today we are starting the graduate schools. We will tomorrow morning is uncertain what's going to happen, but anyway, for the moment, we're beginning the graduate school and configuration spaces with Ben Knudsen, who will talk, I guess, 2 hours today, 2 on tomorrow, and 2 on Friday. And the schedule is now in his hands. So,
also a special welcome to all of you who are attending online. Please feel free to ask questions at any time. And to those of you in the audience, if you have, we welcome questions. It's through questions that we learn what this is all about. But if you'd like to ask a question, please try to wait for the microphone. Otherwise, you shut out all our online audience. They don't hear the question. So if you could just ask for the mic, I will get it to you as fast as I can. Okay, well, welcome, Ben, and we're going to start our first lecture. Thank you very much.
I haven't done anything yet. Thank you for the invitation. Thank you for the invitation. Thank you for the introduction. Thank you all for showing up. I'm really excited to be here. Not just because it's fun to hang out with you all for a couple of days, but because Fred Cohen, although I was never fortunate enough to meet him, is probably the #1 mathematician, either on whose shoulders or in whose shadow I've been standing, basically since 2 or 3 years into grad school. Extremely important for me. So it's just a real honor and a pleasure to be here to be able to talk about a lot of the math that he really pioneered and loved. I'm going to be telling you stories for at least the first 2 days solid or more. And most of them he either discovered or influenced heavily. So he's all over this stuff. Please do interrupt me at any time. Okay, so what's this stuff? This stuff is configuration spaces. So let me just give you the definition that we're going to be working with. So the configuration space of K ordered particles in a topological space X, I'm going to call Fk. There are approximately as many notational traditions as there are authors on the subject. There might actually be more. I'm going to use, this is almost Fred's notational convention. So this is just the space of K points in X that are all different, right? Very simple. So K tuples, none of which are the same. I might refer to these coordinates as particles. I'll draw a picture in a moment that looks like particles, and then you'll say, ah, yes, particles. This is the ordered configuration space. The unordered configuration space I will call BK, and that's the quotient of the ordered configuration space by the obvious action of sigma k that permutes the labels. Okay. So simplest thing in the world to define, not always the simplest thing to study. So just a couple of pictures to help us think about what's going on. So here's the torus, and here's 3 particles, 1, 2, 3. And this is a picture of a point in the ordered configuration space of 3 particles. Yeah. Here's another topological space. It's that graph. It's the cone on a discrete space with 3 elements. And here's a picture of a point in the unordered configuration space of that graph, which I will call S for star 3. I'm not going to talk about that kind of thing until the last day, probably. I mean, maybe not at all. Who knows? We'll see how fast I go. Maybe I will. Let's go this way. Great. So configuration spaces. There are lots of reasons to care about configuration spaces, and I'm not going to tell you about any of them. But if you care about anything, then you also care about configuration spaces. That's how God made the universe. So if you like homotopy theory, if you like knot theory, if you like embeddings, if you like mapping class groups, if you like number theory, if you like robotics, Hamisha, then you like configuration spaces. Okay, and I'm not going to talk about any of those things. I'm an algebraic topologist, confession, and so I'm going to talk about the algebraic topology of these spaces. So we're going to adopt an axiom, which I will attribute in honor of the occasion to Fred. And the axiom is that configuration spaces are interesting. There's lots of reason that you should adopt this axiom, but I can't force you. That's the way with axioms. And so our goal, because I, and therefore by association you, we are all algebraic topologists, at least for today, is to do some calculation. Okay, so that's the plan. Mostly we're going to be talking about cohomology. You were going to, and you may still, depending on fate, hear something about the fundamental group at some point. But I'm not going to tell you much about the fundamental group. Okay, so let's get started. Let's look at an example. This is the most basic example you could possibly. Well, it's not. That's a total lie, but it's pretty basic. So let's look at 2 particles in Euclidean space. Yeah. So here they are. Those are my 2 particles, 1 and 2. So what are the things about those particles? The things about those particles are their center of mass and how far they are from the center of mass and what direction you go to get from particle 1 to particle 2. Yeah. And if you tell me those 3 pieces of information, then I can reconstruct the configuration of 2 particles completely. So that's saying that this space is homeomorphic to a copy of Rn for the center of mass times a copy of the positive reals for the distance times a copy of the sphere of the appropriate dimension for the direction. In particular, it's homotopy equivalent to just a sphere. And the map that witnesses that homotopy equivalence, I'll call gamma. And it takes the configuration x1, x2, and sends it to the unit vector between them. So x2 minus x1 divided by the length of x2 minus x1. This is called the Gauss map. Okay, everybody on board? Very simple example, but extremely important. We're basically going to be squeezing this one example for an hour or 2. Okay. Having this example of two particles, you might want to try to bootstrap from there. And in fact, we can do that. And the thing that lets us do that is the first theorem that was ever proved about configuration spaces, which maybe is the most important theorem that has been proven about configuration spaces. I don't know. It's used all the time. So it's the theorem of Friedel Neuwirth. And it says that if you have a manifold, it's crucial that it is a manifold. So M. So manifold of dimension at least 2. We're going to talk about what happens in dimension 1 on the third day. Again, if I move fast enough, everything today is going to be about dimension 2 and higher. Then what the theorem says is that the map that takes a configuration of k particles and projects off the last one to get a configuration of k-1 particles. X1 k is sent to x1 through k-1 is actually a fiber bundle. What's the fiber? Well, if you look at these particles, x1 through xk-1, and you keep them fixed, and you ask, what is the space of possible xk's that there could have been? It's just the complement of those particles in M. Right? And already you see that it's crucial that it's a manifold, because manifold minus k-1 points is well defined as long as the manifold is, I guess I need to say connected. But other random space that's not a manifold minus k-1 points is certainly not a well-defined thing, because it depends on where those particles were. Okay. So the fiber is M minus x1 xk-1. Okay. So that's the theorem. Are there any questions about what the theorem says? It's not a particularly difficult theorem. It relies on some basic manifoldy type things. I'm not going to say anything about the proof, but it's not, you shouldn't feel scared by it.
Questions, you need to be less clear.
Oh, that will happen naturally as time goes on. So a few immediate corollaries of the theorem. So, or near enough to immediate. So as long as I and n are greater than 1, we can calculate, well, we can't calculate, but we can say exactly how much we can't calculate the higher homotopy groups of the configuration spaces of Euclidean space. So pi I k of Rn is expressible in terms of homotopy groups of spheres. So it's isomorphic to the direct sum. What do I want to call this? I guess I want to call this L. L ranges from 1 to k-1 of pi I, a wedge of L many n-1 spheres. And we can't calculate this, but we've expressed this in terms of that. So that's some kind of progress, I guess. Why is this a corollary? Well, you can look at the long exact sequence of the fibration, argue by induction, and easily produce a section of the fibration by adding your kth particle very far away from the k-1 particles. Okay. So not too bad. Another corollary, and I think these two things are all I'm going to say about homotropic groups the whole time, is that if M is an aspherical surface, then its configuration spaces are also aspherical. So K of M, Fk are aspherical as well. Most of the surface is very spherical, of course. And so what this means is that the fundamental group of the configuration spaces in these cases completely determines the topology. And these are the famous braid groups of the space in question. So, so away from homotropic groups, let's try to calculate something we can actually calculate. So the idea this theorem suggests an inductive argument, right? And so the idea that we'd like to pursue is to calculate the cohomology of the order configuration spaces of Rn inductively. And so what we need is a tool that tells us about how cohomology is related in a fiber bundle. And you can take your pick. The tool that I'm going to use is called the Luray-Hirsch theorem. So let me remind you what that says. So the Luray-Hirsch theorem is about a fiber sequence. So let's say we have a fiber sequence that looks like that: base space B, total space E, fiber F, and they're all path connected. Of course, if E was just the product of B and F, then we could calculate the cohomology of E using the Kuhn theorem. And so what the Luray-Hirsch theorem is a criterion for the cohomology to be that simple and not more complicated. Okay. And the criterion is if the cohomology of the fiber is free, by which I mean free abelian, and the induced homomorphism from the cohomology of the total space to the cohomology of the fiber is surjective, then actually the cohomology of the total space is isomorphic to the tensor product of the cohomology of the fiber. It doesn't matter. Cohomology of the base with the cohomology of the fiber. Of course, if E was the product, then this would be an isomorphism of rings. That's too much to expect, but it is an isomorphism of modules over the cohomology of the base. Okay. So this also is not so difficult to prove once you have the Serre spectral sequence. If you know the Serre spectral sequence and you don't know the Luray-Hirsch theorem, then it's a fun exercise to prove the Luray-Hirsch theorem from the Serre spectral sequence. Integers. Oh, the question was what coefficients are we talking about? And I'm talking about integral coefficients. It doesn't matter. Other questions? Okay, so the important thing in using the Luray, difficult to say that 30 times fast, the Luray-Hirsch theorem, the key player is the cohomology of the fiber. It features in both of the conditions, right? And in our case, we're looking at manifold equals Euclidean space, and we're trying to use this vibration. And the fiber in that case is the complement in Rn of k-1 particles, points, k-1 points. So let me just draw that. Maybe my k-1 points are these ones. There's 1, there's 2. There's point I. There's k-1. Okay. So this is the complement of x1 through xk-1 in Rn. Of course, we all know that that space has the homotopy type of a bouquet of spheres of the appropriate dimension, and deformation retracts down onto a bouquet of spheres. And in particular, we can say exactly what a basis for the homology or the cohomology, but I'm going to talk about the, let's back up for just a second. How would we know if the cohomology was free? Well, I guess we know, because the space is a wedge of spheres. Great, check. How would we know that the induced homomorphism on cohomology was surjective? One way to do that is to get a nice homology basis and then try to detect that homology basis. Okay, so that's what we're going to do. So that's why I'm talking about homology all of a sudden. So of course, a basis for the homology of this space comes from the Hurewicz image of some embeddings of spheres. There's the embedding of a sphere that is a small sphere around this missing point. There's the embedding of a small sphere around this missing point, and so forth. Okay. If we're talking about configurations, a small sphere around particle I, which is stationary, is particle K allowed to be anywhere on that sphere around particle I. Yeah. So a good homology basis looks like, you know, I don't know, like that. There's particle K, right? So all of which is to say the homology of the complement is free on the Hurewicz images of several embeddings of spheres. Which ones? I'll call it iota I. So that's an embedding of an n-1 sphere. And all I do is I identify that n-1 sphere with a small sphere around, you know, the boundary of an epsilon neighborhood around point I. And then include that into okay. And so if we want to know that the homomorphism from the cohomology of the total space, the configuration space, onto the cohomology of the fiber is surjective, what we should do is we should try to come up with cohomology classes in the configuration space that detect those homology classes. Yeah. If we can do that, then we win. But that's actually not so hard to do given ideas that actually are already on the board. The ith one of these homology classes is about the direction effectively between particle I and particle K. We already know about the Gauss map, which is precisely measuring the direction between two particles. Okay, so so an exercise. I was told this is a school, so I'm going to give you a lot of exercises. I'm not grading them though. So let's just adapt our notation right there. So gamma AB is going to be the map that takes a configuration and spits out the unit vector between particles A and particle B. Then what we can do is we can look at the composite, which is our embedding iota described over there, pictorially and in words, to the configuration space. I guess I should be slightly more pedantic. Strictly speaking, iota is an embedding into the complement of into the fiber, which is not the same thing. And then I can measure the direction between particles A and B, and now I have a map from a sphere to a sphere. Yeah, and what the exercise says is that that map has degree. Oh, I'm sorry. This is supposed to be IK, not AB. JK, excuse me. So embedding of ith sphere, jth Gauss map has degree delta ij. And so what, that was not a question. Okay. I see. So what this tells us is that, in fact, the condition of the Leray-Hirsch theorem is met because what it tells us is that the cohomology classes pulled back from the sphere under these various Gauss maps detect exactly the homology basis that we have constructed. Okay. So Leray-Hirsch applies. Okay, what do we learn from the Leray-Hirsch theorem? Well, we learn the conclusion, obviously, that we have some complicated inductive description, not quite as rings. Like the failure to being a ring isomorphism gets worse as we increase K, right? So we don't just completely win, but we do mostly win. And partial victory is all you can expect in today's economy. One thing we can conclude from, if we sort of stare at this exercise for a second and also stare at the theorem for a second, because we're using only these cohomology classes pulled back from the sphere under these Gauss maps, we can actually conclude that the cohomology ring as a ring is generated by those classes. You can conclude that much. Okay, so in particular, the first conclusion we can draw is that the cohomology of the configuration space is generated as a ring by, I'll call them alpha AB, which is the pullback under gamma AB of the generator of the top cohomology of Sn, which I will just call 1, I guess. Maybe I'll call it bold 1, so you know it's bold. Okay, so we have a collection of generators for the cohomology ring. That's good. We also know the rank of the cohomology. We know that it's free abelian inductively because we're tensoring together a bunch of free stuff. And we can say what the rank is. So I will encode the rank in the Poincare series of the space. So which is just the generating function of the Betti numbers. So the Poincare series of the configuration space we can show inductively is just because we're taking a tensor product that corresponds in terms of Poincare series to taking a product of Poincare series. And so we are just multiplying on the Poincare series of a wedge of spheres, which is like a pretty simple series, right? And so what you get, if you think about it for a second, is you get a product from 1 to k minus 1 of 1 plus L times t to the n minus 1. I guess I should have a t here. Okay. So again, the coefficient of t to the whatever is in this series polynomial is the rank of h whatever. Okay. Maybe I'll pause for questions at this point.
How does this say?
Yes. So one of the conclusions of the Leray-Hirsch theorem, which I didn't write here, is that the cohomology is free. So the Poincare polynomial is independent of the ground ring. Other questions? Groovy. Okay. So we have generators, and we would like to know what the cohomology ring is, right? So that means you need to start multiplying together things and like see what happens. Right? So here's another exercise. It's about relations in the cohomology. We have generators, we need relations. So one easy relation, the relations come in 3 flavors. 2 are easy and 1 is not, but less easy. One relation is that alpha AB squared is 0. Of course, because that's already true in the sphere, right? Top cohomology of a sphere squares to 0. Okay. Another relation is what happens if you switch these indices. Well, you pick up a sign, and the sign you pick up is -1 to the dimension of the Euclidean space that we're talking about. That's ever so slightly less obvious than the first relation. This comes from the fact that interchanging the 2 particles corresponds to the antipodal map on the sphere, which has degree this because it's an n-1 sphere. Okay, those are the easy relations. The slightly less easy relation is about products of the alphas and 3 indices. So it says that if I take alpha AB times alpha BC and add on the ways of writing this after cyclically permuting the subscripts, so that's alpha BC, alpha CA, and alpha CA, alpha AB. So cyclic permutations of ABC, I get 0. Okay. So this is sort of the important relation. It's called the Arnold relation because Arnold discovered it when he calculated this cohomology for n equals 2. Probably I should have said that sooner. Arnold, I'm doing a long storifying of Arnold's calculation for n equals 2 and Cohen's calculation for larger n. You might also think, hey, that reminds me of the Jacobi relation if you've ever looked at a Lie algebra before. And it is that. And maybe I will allude mysteriously more to that connection, but probably not say anything too substantial about it as we go along. Okay, why is this an exercise? Well, it comes with a hint. So it's a relation about 3 particles, A, B, and C. And the first time it shows up is in the configuration space of 3 particles, 1, 2, and 3. So you can reduce to that case easily. So the hint is to reduce to A equals 3. Then do a slight unpacking of our Leray-Hirsch argument or of the slight foiling of the Poincare polynomial to see that the relevant cohomology group in that case, it has rank 2. So show that the rank of H, in this case, it would be 2 times n minus 1 of F3 of Rn is 2. And so what that means is that there is a relation among these 3 things because they are 3 things in a rank 2 thing. Yeah, they could not possibly be linearly independent. And then you can use the action of the symmetric group to show that the coefficients of each of these must be the same. And then we know that there is no torsion, and so the coefficients have to all be 1.
It's a clever.
That's Cohen's argument. Yeah, Arnold's argument is also clever in a different way, which I don't know. I think like there's Russian cleverness and non-Russian cleverness, but I don't know. I don't want to go too far in that direction. He just is like, here's some differential forms that already satisfy the relation. But I wouldn't have thought of that. I might have thought of this, but I would not have thought of that. Okay. Questions about the relations or the? Yeah.
I'd like to ask a question. This is a class. We're asking questions that we learn what's going on. Right? We even accept stupid questions, right? We prefer stupid questions. No, like would anybody online like to ask a question? I guess not.
Okay.
I'd like that action, sigma k in the total space of these vibrations. We're just thinking about the structural group of that vibration.
So I heard 2 different things. One was something about the action of sigma k, and one was something about the structural group of the vibration.
Want you to clarify.
Okay,
question.
so something about the symmetric group. What you can do is you can look at the projection from the ordered configuration space to the unordered configuration space. That's a covering space structure group sigma k. That's thing 1. Thing 2 is the Fidel-Norwitz vibration, which is no longer on the board, which is the coordinate projection from the configuration space of k particles to the configuration space of k minus 1 particles. The fiber, as you remember, is the manifold minus k minus 1 points. There are results about how far you can reduce the structure group of that vibration. And I don't know them well enough to quote them. Of course, so I think, so certainly, yeah, no, I don't remember. You can reach to the diffeomorphisms. In the case of Rn, I think you can go farther, but I don't remember. This is all in Fidel Husseini's book. Yeah, I've never even needed to care about that vibration as more than just a vibration. So the structure group has never been relevant to me. Sorry not to have a better answer.
I thought it might have a role in this last article.
No. But the action of the symmetric group absolutely has a role.
Anybody else? Okay, thanks.
Okay. So where we are headed, as anyone would guess, is the theorem that, in fact, these are the only relations. So the cohomology of Fk is generated by the alphas subject only to these relations. Okay. So again, Arnold proved this for n equals 2, Cohen for all other n. The argument I'm going to give is more following an exposition of Devsinha's, which I quite like. And again, this is n greater than 1. The situation is different and considerably simpler for n equals 1. Okay. So the goal, how do you prove something like this? You have some generators and you have some relations, and that buys for you, by the magic of universal properties, a homomorphism from the greater commutative algebra abstractly presented like that to the cohomology ring. And then you just need to show that that homomorphism is an isomorphism, right? And that homomorphism being an isomorphism has nothing to do with rings. So it could be really useful to have a basis. So that's basically the kind of argument we're going to give. Okay. So toward a basis is where we are headed now. Is everybody on board with the strategy? Okay. So what we are going to do is we are going to adopt a small graphical calculus. We're going to represent words in the alphas as graphs. Okay, more precisely as directed graphs. More precisely as directed graphs on the vertex set 1 through k with edge orderings, or an ordering on the edges. But I'm mostly going to keep that kind of, it's not really polite to talk about those things. So what do I mean? If we have alpha AB, we could think of that, as we already did, as an edge from A to B, right? Because we're measuring the unit vector from particle A to particle B. Most reasonable thing in the world. What about a product of two? So like alpha A, B, alpha B, C, then surely we would represent that like that, maybe. Okay. And where the edge ordering comes in is this is the first edge and that's the second edge, because I wrote this first and then this first. So don't worry about it. The edge ordering is just what order you write the alphas in. We're not gonna worry about that. Everybody on board so far? Here's another thing you could try to write down: alpha AB, alpha AC, alpha AD. Why not? Well, all of these are connected to A, and so that's going to look something like that, I guess. So there's A, B, C, D, and the arrows are all pointing out. And another thing you can do is you can multiply alphas that have nothing to do with each other, alpha AB and alpha CD, and you can represent like that. Okay. And the only thing that's a little bit ambiguous about this is that alpha AB is defined in every configuration space from 2 onward. Well, depending what A and B are, I guess. And so, strictly speaking, there are silent 0-valent vertices here that pad things up to K, if you really want to be precise about it, which I don't, and I'm going to ignore those forever. And if you, one other thing that will help you stay sane is to try to remember what degree things are. The degree of one of these expressions is n-1 times the number of edges, because there's one edge for every element. Okay. Okay, so then the lemma, yeah. Thank you. So the lemma is that the cohomology of the configuration space is spanned. We know it's spanned by all possible products of the alphas, but now we are reducing the spanning set down to a more manageable size. Spanned by graphs that I will call long, because that's what Dev calls them. Long graphs. And I'll say what that means. So i.e., how does a graph count as long? Each of its components should be linear and have some other properties. So graphs with components of the form there's I1, there's I2, probably doesn't matter. Let's call this IR-1 and IR. So a linear graph. All of the directions are that way, in the linear direction. How do you know which way is that way rather than this way? Well, part of being long is that the first vertex should be the least vertex, least among the vertices in the component. Okay, with I1 minimum. And the edge ordering should be also linear, but we're not going to worry about the edge ordering very much. Okay, so everybody on board? So graphs on vertices 1 up through K, each component is linear, and the least vertex in the component is all the way at the bottom of the graph. Okay. Or maybe put one more thing on this board. So the idea of the proof, which I will not give in detail, but I'll give the idea and I will doodle a little bit to yes.
Can you explain what the eyes are again?
Yeah, so we're representing a cohomology class by a graph with vertices 1 up through k, k being the number of particles. And so I1 through IR are just numbers 1 up through k, all distinct. And outside of this component are like other components that have the rest of the numbers. Does that make sense? Awesome. So I'll give you an idea and I'll give you some pictures that will probably convince you. The idea is that you can use the Arnold relation, the only interesting relation, to reduce the valence of a vertex. And so you start with the component. You can't ever change the number of components with the Arnold relation, so you're stuck with that. You can start with a component and start with the least vertex in that component and just use the Arnold relation until it has valence 1. And then you go to the vertex that it connects to. Well, you can't make it have valence 1 because you already did that to this one, but you can make it have valence 2. And then you can just keep going forever. Okay, that's the idea. So use Arnold to reduce valence. Okay.
Could you just remind us of the Arnold relation?
Yes, I'm going to do that. I'm going to do it in a different way than I did before, which will either be. I'm sorry. So let's look at an example. So let's look at the example, this graph. Okay. So we're going to start with vertex number 1, and we're going to try to reduce its valence. Okay. Now, what the Arnold relation says is the relevant part of, well, I could choose a different choice, but an Arnold relation is alpha 1, 2, alpha 2, 3 plus alpha 2, 3, alpha 3, 1 plus alpha 1, 3, alpha, 1, 3, alpha 3, 2. No, total nonsense. Alpha 3, 1, alpha 1, 2. There we go. And this piece is talking about 1, 2, and 1, 3. So 1, 2, and 1, 3. And so what I can do using the Arnold relation, after some signs that I'm neglecting anyway, so let's not worry about signs, is I can replace this picture with 2 other pictures. Right? And so what are my 2 pictures? My 2 pictures are, well, I have the same vertices, and it's about cyclic permutations, right? So I should just permute what's happening with the vertices cyclically. So this edge stays the same, and then I'll have that, which is already linear. It might not have all of the properties, but it's linear, and again, that edge stays the same. And that's the other cyclic permutation, which also is linear. May not have quite the right properties, but it's getting better. Okay. And then we keep going. Okay. So if you follow this example through, you'll end up with a sum of 6 terms, 6 long graphs with signs. But nevertheless. Okay. Great. So now we have a smaller spanning set, right? We have reduced our spanning set from all products of the Arnold classes to just the long graphs, which, spoiler, are a basis, but we don't know that yet. Yes.
Is the I1 minimal in this component or
in the component? Yes, minimal in the component. That's right.
Thank you.
I think they saw another hand. No, I guess not. Okay. Okay.
We have a question online. As a ring, the cohomology is generated by the question. Spanned means generated as a ring, right? Yes.
So if the question is,
It's a question about what the meaning of spanned is.
just get closer so I can read. Spanned. I think the question is, what is the sense of the word spanned in this lemma?
Yes, that's right.
Thank you for that question. That's a good clarification. The sense of spanned in this lemma is as an abelian group. Okay. I will always use span to mean linear. I may use generate to mean either linear or multiplicative. Does that answer your question?
You're okay, yes. Okay, thanks.
Okay. Great. The other question is thank you.
Yeah.
Okay, so so we don't know that it's a spanning set yet, but sorry, we don't know that it's a basis yet. We do know it's a spanning set, and we do know the size of a basis in the sense that we know the Poincare polynomial, right? So we're not too far.
Is the point of this that it's a basis? Because if you simply wanted to prove the theorem, you could just count. Like
that's what we're doing.
Where you're going to prove that this is a
Yes.
basis, but
Yes, we have not. That's what I just said. We have not yet done that.
but the point is that not just that you prove the theorem, but that you actually get a basis as opposed to, well, the theorem only says that it is generated, right, by these things. Okay.
So they are two different and a priori completely unrelated facts. So this is a presentation as a ring. That's a valuable thing to have. That's not better or worse than having a basis. We are going in the process of proving this theorem to exhibit a linear basis. That's also a good thing. Yeah. That probably is, but I don't know. Well, I mean, okay, I threw in all of the alpha ABs, so. Okay. Maybe I will abbreviate this next part. How do I want to abbreviate it exactly? So let's write GKS for the number of long graphs with K vertices and S edges. And let's write capital G. Let's let it be the generating function of those numbers. So this will be the sum over S of GKS T to the S. Remember, up to a factor of n-1, the number of edges is the homological degree. So it's sensible to have S, the number of edges, as the exponent here. The exercise, which you can think about, is I will write it and then I will raise the board so that folks can see is that we have a recursion on these numbers. So GKS is equal to GK minus 1 S plus K minus 1 times GK minus 1 times S minus 1. Excuse me. Okay. And as a corollary, we can factor the generating function of these numbers in a strangely familiar way. So as the product from 1 to K minus 1 of 1 plus LT. Oh, it's mixed up. Um, so now we can prove the theorem. So let's prove the theorem. So by the lemma and the corollary, or rather, sorry, by the corollary, we're not using the lemma yet. The rank of h n minus 1 times, or let me write it this way, s minus 1, or, oh, sorry. Let me put it this way. The Poincare polynomial, which we've already calculated, of the configuration space is the same as this polynomial with a slight change of variable. So it's equal to gk of t to the n minus 1. Okay. And so that tells you that the rank of the cohomology is equal to the number of long graphs. But we know by the lemma that the long graphs span, and so that means that the long graphs form a basis. Long graphs form a basis. Okay, how does that help us? Well, it turns out that, or we can just observe that this argument that proved the lemma only used the Arnold relation, which holds in the ring abstractly generated by the alpha subject to the Arnold relation. So the same argument that proved the lemma about the cohomology proves the lemma about the ring abstractly presented. So long graphs form a basis for that, or excuse me, long graphs span that ring. And so what we have is we have a ring with a spanning set that maps to this ring and maps that spanning set onto a basis. And it's an easy exercise to show that under those circumstances, it has to be an isomorphism. So maybe I'll just say the rest is an exercise. Questions about any of that?
Questions? Any online questions?
So if there are no questions, I have a question for you. This is a democracy after all. My understanding of the rules, and correct me if I'm wrong, my superiors will correct me, is that we get to decide how long of a break we have. In the schedule, it says a half an hour. I've been to a lot of conferences. Half an hour breaks have often felt rather long to me, but you might not have that experience. So we could have a break from anywhere from, I would say the minimum viable break is probably 15 minutes to half an hour. Show of hands, who is more in the 15-minute camp? Who is more in the 30-minute camp? Sonder, you don't have to come back. We're going to have a 15-minute break, so we're going to start again at 3:50.
Very nice.
Oh, thank you.
Thanks very much.
Glad you're enjoying it.
Yeah. um,
For an example,
How's that?
Hello? Hello, hello. Testing.
Okay.
Great. Sorry about that. So to fill in the folks online, what we're trying to do now is we're trying to use our calculation of the cohomology of the ordered configuration space to learn something about the unordered configuration spaces. So the projection map from the one to the other, the quotient map, is a regular covering space with deck transformation group, the symmetric group for reading the particles. So that tells us right away that we can understand the rational cohomology of the unordered configuration spaces somewhat easily, or at least there's a simple formula for it in terms of what we have already calculated. Actually, parsing that formula may take some work. Specifically, what we learn is that the cohomology of the unordered configuration space rationally is isomorphic to the invariant part of the rational cohomology of the ordered configuration space via the transfer. Okay. Okay, so what that means is, at least if we want to understand the rational situation, we understand this rationally very well. We just calculated the cohomology ring. We know it's free of abelian. So this is just what we calculated before tensor but Q. So it's still generated by the alphas, subject to those relations, just over Q now. So if we would like to unravel what this is, we have to understand the thing that we already understood, but now no longer as a ring or as an abelian group, which is how we've understood it so far, but as a representation of the symmetric group. Okay. Okay. Well, what can we say about that? Of course, our long graphs basis is no good. Or, I mean, it's great. It's really good, but it's not equivariant. It's not invariant under the action of the symmetric group. As soon as I start acting by the symmetric group, do I have the long graph? I have the long graph. I'm acting. Oh, I1's no longer minimal, right? So the action destroys this basis. However, when I permute the labels, I don't change the shape of the graph, and I don't change which particles are in which component of the graph, right? So what we can say is that I do change. What I just say is completely wrong. That's exactly what I change. I change which particles are which component of the graph. What I don't change is how many vertices are in each component. I can't change that. I change their labels, but I don't change sort of the structure of the graph. So all that is to say that a graph determines a partition of the number k, by which I just mean a list of non-zero numbers that add up to k, by convention listed in descending order. How does it determine a partition of k? It's just the count the number of vertices in each component, because this is a graph on k vertices. Okay, and that partition, that signature of a cohomology class, is invariant under the action of sigma k. Okay, and this partition is preserved by the action of sigma k. Oh. Maybe that was not maybe that was not clear to those online. What just happened? They're working on it.
They only sent 2 boards.
I understand.
Somebody in the other room is supposed to be moving it so they see the correct board.
I understand. They might not understand. That's why I was telling them. Are there questions? Shall I continue or shall I wait, do you think?
They can see the route.
Oh, yes. Thank you. Thank you. What's your name? I'm sorry?
Andre.
I'm going to call you Andre.
Okay.
Is that close enough?
Yeah.
Okay. It's probably not close enough. I'm sorry. Thank you, Andre, for your observation. Yes. So just to give you an example of what I was talking about, hopefully this will clue in the people online this example. To a graph, we are going to associate a partition. And so, for example, there's the graph with no edges. And that graph will be associated with the partition 1, 1, 1. There is the graph with 1 edge on 3 vertices, and that will be associated with partition 2, 1. And there's the graph with 2 edges that will be associated to the top partition. Okay. Is everybody on board so far? So far what we're saying is we have this basis, and more generally we can describe a cohomology class as a graph, and we can associate to that graph a partition of the number of particles, and that's preserved by the action of the symmetric group. Let's keep doing that. So is there a question? Okay. So the upshot of this is that if we write L lambda for the span of all long graphs partition lambda, then we have a decomposition of the cohomology that is a decomposition of representations. So what we proved before without knowing it is that we have an isomorphism between the cohomology of the ordered configuration space and the direct sum over all partitions of K of the sub group L lambda. And this is an isomorphism of sigma K modules. The letter L stands for Lie. So I promised you I was going to gesture mysteriously in the direction of Lie algebras from time to time. I'm now doing it. Questions at this point? Okay, so what observation number one tells us is that we need to try to come to grips with this sigma k representation L lambda, right? If we look at the invariant part of this, it breaks up as an into a direct sum of the invariants of the L lambdas. And so we need to try to understand the invariant part of L lambda, at least rationally. That's what we need to do. Okay, well, I don't know how we're going to do that, but maybe we can just try to point to some elements that are in L lambda given a partition. We have a partition lambda, which is lambda 1 through lambda r, then they're somehow the most obvious elements of L lambda. If I handed you a partition and I asked you to write down an element in L lambda, probably what you would do is you would take the first lambda 1 labels, and you would put them in the first component of the graph. And then you would take the next lambda 2 labels and put them in the second component of the graph. That's what you would do. Tell me you would do otherwise. I defy you. So the most obvious elements of L lambda have the first lambda 1 labels in the first component, and so on. And so what that's saying is that inside of L lambda, or rather at least mapping to L lambda, but it turns out inside, that's not so hard to see. Inside of L lambda, we have a copy of the tensor product of these things. So if I say I'm going to take the first lambda 1 labels and put them in the first component, then that's talking about L lambda 1. And if I'm taking the second batch of labels and putting in the second component, that's talking about L lambda 2. And if I do that for each piece of the partition, that's talking about taking a tensor product. Okay, so in other words, what we just described in words is a construction of a homomorphism from this tensor product to the module that we care about. Okay, which is definitely not equivariant for the action of sigma k. Why is it not equivariant for the action of sigma k, you might ask? Well, sigma k doesn't even act on this, right? The thing that acts on this is the product sigma lambda 1 times sigma lambda 2, right? And it is equivariant for that action, right? If I permute the first lambda 1 elements, that's the same as permuting them inside of L lambda, no problem. I view that permutation of the first lambda 1 labels as a permutation that happens to fix everything else, no problem. Okay, so didn't quite leave myself enough room. We obtain a homomorphism like this, which is equivariant for the product of the smaller symmetric groups. Right. It's actually even more equivariant sometimes. So to give you an example, let's look at let's look at this partition of 4. So the partition 2, 2, right? So if I did my construction, what I'd have is a map from L2 tensor L2 to L22. And what we've said so far is that it is sigma 2 times sigma 2 equivariant. And that's true. But it's more than that, because another thing I can do is I can switch the copies in the tensor product. And it's equivariant for that action too. So it's actually equivariant in this case for sigma 2 wreath sigma 2, the wreath product of sigma 2 and sigma 2, or the semi-direct product of sigma 2 and sigma 2 squared. Those are the same thing. Okay. So in fact, let me erase this, which was true, but there's something better. So it's equivariant for the action of sigma lambda, which is what I will call it. Sigma lambda is a subgroup of sigma k. And what sigma lambda is the stabilizer of the set partition. Right? So the graph where I put lambda 1 through lambda 1 in the first component and the next lambda 2 of the labels in the second component, that's actually telling me a partition of the set 1 up through k by the components of the graph. And that's a partition of the set. It the set of partitions of 1 up through k carries an action of sigma k. And that particular set partition has a stabilizer group, stabilizer subgroup, and that's sigma lambda. It's always going to be a product of wreath products of symmetric groups. Basically, the only difference between it and the direct product we wrote down before is that whenever there's a repeated number in the partition, I have to stick in a wreath product. That's it. Okay. Action of sigma lambda, the stabilizer of the corresponding set partition. Third question? Yes.
What is a wreath product?
Yeah. So I'll give you an example. Like, we're not really going to care about wreath products. We don't need to, but I can I'll give you an example. Or, I mean, I can also just give you a definition, or a definition that is as general as I need it to be. And I also happen to be dyslexic in only this notation. So it's either that or it's that. I mean, I don't know which, and you can tell me and I will not remember. So whichever one it is, does anybody know which is the correct one? Thank you. We're gonna believe, what's your name? Peter. We're gonna believe Peter. This is Peter's convention. So this is the semi-direct product of sigma r and g to the r, where the action is the obvious action. But this one you can't fool me on. The semi-direct product symbol you can remember, because the semi-direct product symbol has arms, and the arms are what act, right? That's how you remember the semi-direct product notation. This has no way of, there's no impossible. So anyway, it's something like that. I'm sorry? It's one of those theorems you prove in the gym. Okay, so let's just look at a quick example. I won't define sigma lambda in general. Well, I mean, I just did, but I won't. Anyway, so let's look at 7 particles and the partition 3, 2, 2. then what sigma lambda is it is sigma 3 times, and I chose this example because it doesn't matter what the correct convention is, sigma 2 Reith sigma 2. Yeah, okay. And an element in sigma lambda, there's a typo on my notes, but it will not fool me. An element in L lambda, an example of an element in L lambda is the graph 3, 7, 1. Probably doesn't matter, 6, 4, 2, 5. Right? As long as my graph has the components 3, 2, 2, I can put the labels anywhere I want. That's how those are the rules in L lambda. By contrast, L3 tensor L2 twice only contains things that look like the first 3 particles have to be in some order in the first component. Doesn't matter what order they are in the first component. The next 2 particles have to be in some order in the second component, and the next 2 particles have to be in order, in some order in the third component. Does that make sense? All I'm trying to convey 2 things with this example. The kind of thing that sigma lambda looks like generally, it looks like this generally. And given this example, I think you could write down a definition. And I'm trying to convey the difference between a random element of L lambda and a random element of this smaller thing. Is it clear what the difference is? Yeah.
I'm being a bit slow, but when you're acting, so I mean, L lambda is spanned by long graphs, and when you're acting by a permutation, it might happen that the first index is going to be mapped to some other index, and then the first index is not going to be minimal anymore. Is that a problem, or is it not a problem?
It's a problem insofar as it makes our life harder. It makes the calculation hard, therefore interesting. It's not a problem as in like a contradiction. The Arnold relation is an example of this. The Arnold relation is about how you decompose something that looks like that, maybe, or let me say 3, 1, 2. Into long graphs. This graph is not long, right? Because 1 is not at the beginning. But the Arnold relation tells you can express it as a sum of 2 long graphs.
And
so if you what this is saying is that you can take 1, 2, 3, which is long. It's the thing we like, and you can get to the thing we don't like with a permutation.
Mm-hmm.
And that's what makes life interesting.
But then the fact that L lambda is equivalent with respect to sigma lambda is not trivial, in that we need to prove that if we permute indices in one connected component of a long graph, it's going to stay, it's going to have the same shape.
There's a small thing to check there, but it essentially follows by inspecting the Arnold relation. You can't change the structure of the connected component.
I see.
Yeah.
Thank you.
Good question. Other questions? Is there a question over here?
Any online questions?
I think that there might have been an IRL question. No? Okay. Did I make a mistake? Oh, good luck. Do they? Yeah, that's why I adopted the dash. I didn't use it the dash. Oh, I see. This looks like it could be a, yeah, okay, fine. Fine. Okay. Other critiques of my handwriting. We'll be here all day. Don't start. Okay, so the exercise about L lambda is calculating its rank. So the rank of L lambda is equal to a factorial divided by the order of the stabilizer subgroup times product over the entries of the partition of the size of that block minus 1. Okay. Why is this an exercise? It's because it comes with a hint. So the hint is there are sort of two layers. There's the set partition, and then there's the partition of the number, right? And so you can first count set partitions with a particular shape using orbit stabilizer. And that's where this comes from. So count set partitions. Using orbit stabilizer. And then it's obvious, if you think about it, where this part comes from, because if you are constrained to have a certain set partition for your long graph, well, you have to put the least one in each component first, and then you have complete freedom of where you put the other ones, right? So that's an ordering of the non-minimal elements in that component, which is that, and not what I wrote before. Great. Then count long graphs. Fixed. Set partition. Okay. Yes.
Sorry, I think when you started drawing those little graphs, it had some directions on the edges.
I think you're saying there are no arrows on these edges.
Mhm.
You're right. That's an abuse. This was a cartoon and not a proof. So there's lots of information missing from this picture. There's the directions of the edges. There's also the orderings of the edges.
But still, the formula on the of the L lambda is
No
correct.
problem, because you can change the direction up to a sign.
Oh, I
And
see.
you can change the ordering of the edges up to a sign.
Mhm.
So when I write this splits into two things, what I mean is like this is expressible as a sum of these two things with
I
signs
see.
in front of them.
Okay, thank you.
Thanks for that. Other questions? Okay, so why is that exercise relevant? The exercise is relevant because we have a homomorphism from one representation to another representation that's equivariant for a subgroup of the target. And when we have one of those things, we get to say induction. And that's what this proposition is about. If you haven't met induction before, I will tell you what it is, and I don't know, that will help you, I guess. Proposition says that the induced homomorphism induced by this homomorphism from the induction from sigma lambda to sigma k of this tensor product is an isomorphism. And I'll just remind you that if you have a subgroup and an action of H, the subgroup, on a module, then the induction from H to G of that module, and maybe didn't actually leave myself enough room. is, I'll say R for the ground ring that we're working over, which in this case so far we've been kind of ambiguous about, but this is true over the integers, so it's true elsewhere as well. So RG tensored with M over RH. So in other words, we're changing scalars from the group ring of H to the group ring of G. That's what induction is. Okay. Why is this a good thing? The reason this is a good thing is that it breaks the thing we would like to understand. Remember, we have this decomposition of the cohomology of the order configuration space as a direct sum of partitions of K. And what this does is it breaks that thing that we need to understand down into pieces that are sort of understood inductively. Like L lambda I is the top cohomology of the configuration space of lambda I many particles. And so by the time we get to K particles, of which lambda is a partition, we have already understood, unless the partition is just K itself, we've already understood the pieces of this tensor product if we're arguing inductively. So this is something that's suitable for inductive argument. Okay. Questions about the statement has not yet been proven. We are about to prove it. This is an integral statement. Yeah. Other questions?
Are there any online questions?
Okay. The proof is actually very simple. So L lambda is actually a cyclic sigma K module generated by one thing. Because take any graph, take like write down the graph that you think of when you think of lambda without any labelings. Then choose any labeling you want. You can get to any other labeling you want with the action of sigma K. Right? Okay. So this is generated by one element under the action of sigma K. So in order to show surjectivity, we just have to show that one element is in the image. But it obviously is. We like that one element is one of the obvious ones that we wrote down. So the homomorphism is obviously surjective. And then the exercise shows that they have the same rank because it's easy to show that the induction has this rank. So the homomorphism is obviously surjective. And the two have the same rank. By the exercise. Oh, maybe there's some representation theorists / commentatorists in the audience. I don't know. I think I'm given to understand by gossip that L lambda is, or these representations are referred to as tall Wraith higher Lie characters. So perhaps some of you have heard of that, perhaps you have not. I don't have much connection to that world, but in case you do, that might be helpful to you. Okay. Questions? Okay, let's remember what we're trying to do. We're trying to, is it on the board anymore? No, it's not. We're trying to calculate the rational cohomology of the unordered configuration space. And for that, what we needed to do was we needed to take this and tensor with Q and calculate the invariance. We broke that into a bunch of pieces. So we need to take each of these L lambdas, tensor with Q, and calculate invariance. And now this further decomposition is going to help us calculate the invariance. Okay. So now we come to the invariants themselves. So the lemma is, let's be a little agnostic. So let's fix a field F. And let's say the characteristic is not 2 or 3. And let's say that we have more than one particle. Then we can calculate the invariance after tensoring with F of these basic atomic building blocks. So LK. And the invariants are quite simple. It's just a copy of the ground field if K is equal to 2 and N is even. And otherwise it's 0. So this is this is actually a result due to Fred Cohen in his thesis work calculating the mod P cohomology of configuration spaces and then applying that to power operations on iterated loop spaces. He has like a trio of named theorems in that calculation. We're going to hear more about that calculation later. This is what he calls the invariance theorem for obvious reasons. The proof that I'm going to give is not his proof, for at least for the reason that I have never been able to read his proof and understand it. Okay, we're going to do it in a way that avoids some of the messiness that he is forced to grapple with. Before we prove it, are there any questions about? I see some faces that could be various emotions, and one could be confusion. So, yeah.
L with the subscript K in parentheses. What does it mean?
So this is the partition of K, which is just the number K.
Okay.
And so this is the submodule of cohomology where it's a single component of the graph and all the labels are on that component. Yeah. It's also the top degree cohomology.
I lost track. What was N?
N is the dimension of the Euclidean space.
Okay.
Yeah, we haven't seen N in a long time. Thanks for that question. Other questions? I think there's a question next to you.
Does the fact that you eliminated 3 have something to do with the length of the Harnault relation? Like why this is, maybe I should wait till you've done the proof, but
you're asking me to spoil it.
Oh, okay.
Well, like,
I won't.
No. I was told, Tony told me that questions are worth $100. Everyone who asks a question is getting paid $100. So, because I have to make some money off of this gig somehow, I'll ask you. We'll prove it, and then I will ask you, does it have to do with the length of the Harnault relation? I think the answer will be yes.
So I've lost track of the coefficients. I mean, why were the rationals forced on us?
The rationals were not forced on us. And in fact, we will spend probably all of tomorrow away from the rationals, depending on how far we get. The rationals is just the easiest case. So for the rationals, we can actually calculate the cohomology of the unordered configuration space as the invariance. That's what's special about the rationals, because that's true as long as the deck group is, the order of the deck group is relatively prime to the ground field, the characteristic of the ground field. And that's always true in characteristic 0. So the same calculation would work for like a few primes, but in general, for a general prime, you don't have that. You have the Cartan array spectral sequence, which we'll get to. Yeah. Other questions? Okay. So as a corollary of the lemma, before we prove it, excuse me. That's probably really loud for everyone online. I'm sorry about that. As long as we have at least one particle, the configuration space of one particle is just Euclidean space. We know that cohomology. We can say what the rational cohomology of the unordered configuration spaces are. It's also quite simple. So there's a copy of Q in degree 0, of course, because the space is connected. And the only other non-zero cohomology is in degree n-1 when n-1 is odd. So when n is even. And it's 0 otherwise. So in other words, rationally, these spaces look like either a point or a sphere of the appropriate dimension. Okay. I should have possibly emphasized this. So when n equals 2, we said earlier that these spaces on the order configuration spaces are aspherical. So they're k-pi1s. They're determined by their fundamental groups. And so all of this cohomology that we'd be calculating in that case is group cohomology, algebraically defined group cohomology, if you're familiar with that. And so the calculation we did for the ordered configuration spaces is the calculation of the integral cohomology of the pure braid groups when n equals 2. And this, when n equals 2, is the calculation of the rational cohomology of the braid groups. Yes. Yeah, thank you for that question. I was trying to say several things as concisely as possible. What I mean by this is when n-1 is odd, then when I equals n-1, we have a Q. Okay. There's a little bit of unraveling to get from this lemma to this corollary that I'm going to skip for the sake of time. It's not difficult. Basically it's all there. So we'll just say that we'll say we know. An observation to make before moving on is that if we group all the configuration spaces together. So if we say B is going to be the disjoint union over all K of the BKs, then what this calculation is saying is that the cohomology of this graded space has a particular form that we are not really justified in writing this way, but we will be justified in writing this way later. So if n is even, it looks like a polynomial ring, tensor, and exterior algebra. And if n is odd, it just looks like a polynomial ring. So if it's even and is odd. And the way that you make sense of this is that this cohomology, because the space has a grading, this is now a bigraded object. So it has a grading by cohomological degree and a grading by number of particles. And this generator X has bidegree, homological degree 0, cardinality degree 1, and this generator Y has homological degree n-1 and cardinality degree 2. So this is a compact way of collecting these individual calculations. And we have no justification for writing it because we don't have an a priori ring structure on this object. But it sure is tempting to think that there should be one, and there is. So this will be to be continued. Is a question?
Is there any reason to believe up to this point that there's torsion in that on the space? Any reason to think that there isn't torsion?
Yes. So we're in k equals 2. The configuration space is projective space of the appropriate dimension. So there's 2 torsion for sure. I didn't say that exactly. I said something like it. We don't have any actual reason to think that there's odd torsion, really, but there is. Yeah. Okay. Okay. So you can kind of, in a hands-on way, so what we're going to do now is we're going to prove the lemma. You can do this in a hands-on way for k equals 2 and k equals 3. Because the space in question is 1-dimensional when k equals 2, and it's 2-dimensional when k equals 3. And you can, in the 1-dimensional case, you can just look at it and say that's either the trivial representation or the sign representation. In the 2-dimensional case, you can mess around with the Arnold relation and get some stuff. But higher than that, it's difficult to do by hand. Cohen does it, or at least says he does it. Let me know if you read that proof and you understand it. So we're going to do it a different way. And the problem, if you think about it, because this module is cyclic, we know that the only possible fixed point would have to be the sum of all of the long graphs, the sum of all basis elements. There's at most one fixed point, but the basis, the long graph's basis, has size k-1 factorial. And so doing a direct calculation to check whether a sum of that many terms is invariant under the action of the symmetric group is not something you're going to do easily. Okay. And the issue is that we were talking about invariance, right? We were looking at a sub object. Quotients are a lot easier than subs, right? And so the strategy to do this in an easier way will be to dualize and look at homology and calculate the co-invariance, which is trivial once you have a good basis. Okay, so that's the plan. So we need some homology elements that are somehow dual to the graphs. So here's a construction. Given an ordering of 1 up through k, there is a submanifold of the configuration space in which, actually, let me make my life slightly simpler. Let me skip the ordering part, and then we'll just gesture at that. So what we're going to do is we're going to put particle 1 and particle 2 antipodal to each other on a small sphere. They're allowed to roam around that sphere all they want. So x1 and x2 are antipodal on a sphere sphere of radius epsilon 1. And the center of that sphere is antipodal to x3 on a sphere of radius epsilon 2. And so forth. Okay. Let me draw a picture. And really messed up my ordering of boards. Oh well, we're almost done. So what this looks like is epicycles, if you've ever learned some old astronomy ideas. So x1 and x2 are constrained to be on this sphere. And the center of that is on a somewhat larger sphere, where x3 is antipodal. And the center of that is on a somewhat larger sphere, where x4 is antipodal. And so on. You could keep going. Okay. Is everyone on board with this picture? So what this is describing, this whole picture is allowed to move, right? Like this is allowed to rotate around this larger sphere as long as it stays antipodal from x4, and so on. So it's sort of planetary wheels within wheels. Like the sun is here, we got a planet, and anyway. So what this describes is a map from Sn minus 1 to the k minus 1. That's the number of spheres I need to parameterize this system, to the configuration space. Okay, and it's an embedding for judiciously chosen epsilons, and so I have this embedded torus, and its fundamental class determines a homology class. Okay. So, and of course, more generally, I could choose an ordering, and this could be like I1, this could be I2, this could be I3, this could be I4, and so on. So we're going to use another small graphical calculus. Oh, there's a question? The radii will need to increase. Otherwise, so these particles are never allowed to collide with each other. Otherwise, we leave the configuration space. Yeah. Oh yeah. So if I took the radius of the second sphere to be equal to the diameter of the first sphere, then this particle is not allowed to roam around over the entirety of this sphere, while this particle roams around over the entirety of this sphere without leaving the configuration space. That's a perfectly good submanifold of the product, but not of the configuration space. Does that make sense? Great. Okay. So the image of the fundamental class of this torus, which is a degree k minus 1 times n minus 1 homology class, will denote, again, using graphical, a light graphical language. By the way, this all of this graphical language is sort of Deb Sinha's perspective on homology and cohomology. So I highly recommend you check out his expository paper. It's lovely. So if we think about what this looks like for a bit, we will think that it suggests binary trees. Like here I have a vertex and it splits, and then it splits again, it splits again. So we're just going to denote that homology class using a tree. So we're going to call it the tree with leaves labeled I1, I2 up through I. Okay. So this tree is the name of a homology class. Okay, and just like the more general construction involving graphs, there's a more general construction involving a general binary tree, which you can imagine. If I had a binary tree that split and then split on both sides, then you could imagine a planetary system that had sort of orbits that were that shape. But we don't need that. Okay. So exercise. For you, which is just a beefed up version of something that we calculated close to the beginning, is I have this homology, these homology classes. And let's, because we're thinking about long graphs, let's put the first vertex at the beginning. And then let's scramble the rest of the labels. So I'll choose a permutation sigma in the permutation group of the numbers 2 up through k, and permute the rest of the labels. And on the other hand, I have a long graph that I can do exactly the same thing to using the permutation tau. So I have the long graph, which is 1, sig tau of 2, tau of k minus 1, tau of k. Okay. So this is like a random long graph in LK. And this is sort of not a random one, but a random one of these trees that has 1 at the beginning. Okay. Homology class, cohomology class, I'm entitled to pair them. So if I look at the pairing between this homology class and this cohomology class, I get 1 if the permutations are the same, and I get 0 otherwise. Yeah.
Can I go back?
Yeah.
This one you allow the fourth point to be anywhere on this sphere?
The only constraint on the 4th point is it has to be antipodal to the center of this sphere.
It's possible that the spheres like.
You're worried that like this stack will get so long that it flops over to the other side? That's why we have to choose the epsilons judiciously. So not only do the epsilons have to get smaller, they have to get smaller like fast enough. Yeah. Other questions? Okay, so so our homology classes and our cohomology classes pair together nicely. This calculation is, while slightly more involved, is also just boils down to a series of degree calculations between spheres, just like the one at the very beginning of the lecture. So this is not a deep or mysterious thing. Are there any questions about what it says? Okay, well, yeah.
Why leaving 1? Like, why do I need to having one at the beginning.
So the reason we have the leading ones here is that that's sort of the only way we could think of to use the Arnold relation to get a basis. And the game now is to try to find a dual homology basis. And so if I was going to do that, I'd be like, this is what my graph looks like. I guess I'll try this. And it turns out that this does work. There is a more complicated construction both on this side and on this side. So I can write down for any graph on vertices 1 through k a cohomology class, and I can write down for any binary rooted tree with k leaves a homology class, and I can ask about the pairing of those things, and then they have no relation to each other, and so you're like, I don't know what to expect. And you can write down a formula for that, and that's what Dev does in his paper. Yeah. So this is like a much smaller and easier piece of a larger calculation. Okay, so it follows from this, because these form a cohomology basis, that these form a homology basis. And this is the sort of duality pairing between homology and cohomology. Okay, another exercise. This is quite easy and kind of fun. Is to show that the dual of the, because we now have a pairing between homology and cohomology, and so we can wonder what the dual to the Arnold relation is. And the dual to the Arnold relation is what you would expect it to be, but it's not quite obvious that it is. You actually have to calculate something. So it does involve summing over cyclic permutations on these trees, just like the Arnold relation does. But these two trees are not part of our perfect pairing, or they're not basis elements in our perfect pairing. And so in order to prove this, you have to break them into pieces, or you have to pair them against the basis and see what they evaluate to in order to see how these are linear combinations. Okay. So that's something that you can calculate in a couple minutes on a piece of paper. That's a really good question. I learned it from Dev's paper. Dev says that Fred invented it. Dev says that he saw Fred draw these pictures on a board. So I don't know. More generally, if you have larger trees, say I1, I2, I3, up through IK. This is just one of our homology classes. And I add up the cyclic permutations of just the first three. I also get 0. So I3, I1, I2, IK. So the rest of the leaves are keeping the same labels. I2, I3, I1, IK. The sum of those three homology classes is also 0. That's ugly. Sorry about that. This is not obvious. And this doesn't follow easily from what we wrote down here, or not as easily anyway. There's probably some complicated way to do it. The proposition would follow from the exercise if we knew that grafting trees was linear, right? Because then we could take this relation and we could plug it into this one tree that has like fewer leaves. And then because we plugged in a relation that was 0, we would get 0. But we don't really have any reason to think that grafting trees is linear right now. But it is, and we'll come back to that later. So, proposition implies exercise. Proposition definitely implies exercise. Exercise implies proposition if grafting trees is linear. and that's to be continued. The short answer, if you are familiar with these things, is that grafting trees is a reflection of the operad structure of the little cubes operad. Therefore, it is linear. Okay. I ran out of good chalk. That must mean that I'm almost done. And I am almost done. Are there any questions before we prove the lemma? I'll remind you what the lemma said. Oh, there is a question. I'm sorry, what?
I was asking, are you working over your field F this whole time?
No, like this homology construction is an integral construction.
But in order to infer that from the exercise that your trees give you a homology basis, don't you need to be over a field?
No.
No? Okay. Yeah, thank you.
Other questions? Okay, so proof of lemma. Let's remember what we were trying to do. We're trying to show that L, K, tensor F invariance is usually 0. The calculation of the part where it's not 0 is easy, so we'll just say we're trying to show that this is 0 for K bigger than 2. Okay. Okay. So it suffices to show that the dual of LK tensored with F covariance 0, because this is the dual vector space to this. Okay. This LK dual is just the homology in the appropriate degree. So it has a basis given by these trees. Okay. So the trees above form a basis for LK. In particular, the same observation that we had about LK holds for LK dual, namely that the tree where everything is in order generates as a sigma k module. Right, because I can get any other tree basis element by just permuting the labels. Okay, but now if we let rho be the 3 cycle that permutes 1, 2, and 3 cyclically, raise this a little bit so it's visible. This class by the proposition is annihilated by 1 plus rho squared. And so that means that in coinvariance, 1 plus rho squared times this class is just 3 times this class. Because the relation we impose to go to covariance is that the action of sigma k becomes trivial, right? So it follows that the covariance that we're interested in calculating is 3 torsion, and hence 0, because we're working over a field of characteristic larger than 3. I went 2 minutes over. I'm sorry. I'm done. Thank you.
Very nice. Thanks. Are there any questions?
Two questions. One is reference. So